In this lecture, we will talk about sensory delay, something that is very novel, because with controlling the delay of the response of robots that interact with an environment or with each other or with an external light signal, we can actually tune their behavior in a way that how they actually we can totally invert the behavior. For example, with certain parameters, we can make them go in one direction, and if we invert the change the parameters, we can invert the motion, how they actually behave. This is a kind of a animated picture of multiple robots that are interacting with each other. This was drawn by Mita, the same person that was making the simulations of chiral active particles in the previous lecture. Yes. So, okay, we have a definition of a motion of a robot, and here we see that the robot here is that we have small robots that go in 2 dimensions with a velocity, and they have just like an active particle, they have an orientation that is kind of changing over time randomly. Okay, and this here is we scale this randomness by this coefficient, which is inversely proportional to tau, which makes them kind of you can use this tau later as a kind of velocity decorrelation time, because as time passes, it reorients itself in different directions. Smaller this tau is, what will happen to the orientation over time. If tau is very small, this number will be a lot bigger, right? And the phi will be changing randomly a lot faster. It will decorrelate from its initial orientation a lot faster. If this is very large, it means that this number is very small. Then the orientation of the particle will be changing very slowly. So it will mean that although it will move a little bit randomly right and left, it's for a very long time going in one direction. Okay, this is just and tau is the decorrelation time scale. And now we can have a robot that we actually don't have a constant movement speed. What this robot can do is that it can kind of measure the light intensity in the environment and act accordingly. So kind of let's say if the robot has no, so this is in x-axis, you see here is the intensity of the light that the robot is measuring, the sensors are measuring, and then the velocity as a function of this measured intensity. You see that if we measure no light in the environment whatsoever, then we go with kind of some maximum velocity v0 that we go with, okay? And we kind of rotate around randomly. As we increase, if we observe more and more light in over time, the robot is kind of decreasing its movement velocity to kind of a value that is v infinity, which means that what is the velocity that I would go with if I'm measuring very high intensity light, right? And this is very intuitional, or not intuitional, but it makes sense for a robot, because if it's slowing down, if there is no light measure, it can get lost at an area where there is no signal, right? We want somewhat these robots to be attracted most of the time to the signal, right? Depending on the condition. So this is a kind of good starting point. Is this clear? And this is an exponential decay. I can show you how it is formulated here. Let's see here. Here is how it's formulated. So it's exponentially decaying with I, which is the measured light intensity, and it's starting with V0 and kind of let's see, going down to V infinity. Okay, and this is an exponential decay, and this is a kind of light intensity that the robot is measured. Is this clear? Is it clear also why it's intuitional to have a profile like this? Because the idea is that the robot will not easily get lost with this way, because it's searching more when it doesn't measure any light. So it's kind of doesn't get lost in an area where there is no signal. And of course, we can apply, just like in the case of VCheck model, we can apply these measurements with delay. What we can do is that this is the most fundamental slide maybe of this lecture. So the robot is not maybe adjusting its velocity on, so if we can start with no delay case. So this is the intensity of light that this robot is measuring over time, and this is something random, right? And at a certain time, I measure the intensity right now, right here, and I adjust my velocity in order to, according to this intensity I measure now. This is the case with no delay. We are talking about present time, and we immediately adjust our velocity. The positive delay is also intuitional. What happens is that I keep recording all the intensities I measure at every time step. But when I am going to adjust my velocity, I kind of take the value that I measured in the past, and I adjust my velocity according to this value I measured delta amount of time ago. Is this clear? So I kind of don't forget what I measured. I kind of keep them in a certain memory or buffer or something. Okay, and then I use a past value to adjust my velocity. And there is another type that is called a negative delay in the feedback, which means that I kind of have the structure here, and I kind of estimate from the latest values I measured of the light intensity. This is, of course, can be done with more complicated approximations or extrapolations. You can calculate, for example, take last 3 data, last 4, last 5 data points, depending on how many, what is the frequency of your measurements. And you can make a quadratic or higher order fits to this, or I don't know, any kind of different kind of fits. And you kind of one way, but the simplest way here that we are sticking to is a very simple extrapolation, a linear extrapolation using the last 2 data points here. And we extrapolate the value of the measured intensity to a time in the future. This should actually be plus. I need to write it down. Can you, Giovanni, write it down? This should be plus. I don't know why it's minus, obviously. So is this clear? So for the case of negative delay, of course, we cannot predict or measure the future state of the light intensity, right? But we kind of estimate here. This is kind of similar to the case, for example, if I look at outside now, it's sunny, right? So I say, I don't need an umbrella, right? This is no delay. I look outside now and I say, okay, I don't need an umbrella. I go out now, I don't take it, right? Negative delay is that I looked outside 3 hours ago when I woke up and it was raining, right? And then I didn't look outside after. I was home doing something else for 2 hours, 3 hours. And after that, I'm going out, but I didn't look after again. I say, okay, it was raining. I need an umbrella. I take the umbrella. This is the negative, a positive delay. I have a positive. And negative delay is the following. So it's been sunny, but it's coming very dark clouds. From the behavior of the weather, I kind of extrapolate my idea. Okay, this is not going good. It's going more and more cloudy. Maybe it's going to rain in half an hour. So I might need an umbrella, so I take an umbrella. This is kind of what we are doing here with negative delay, okay? Yes, actually, yeah. It's okay. Okay, yeah. I did it right. Okay, so it's kind of, this is when the delta is negative. This is actually higher than t, so it's okay, right? Okay. So what happens when we have a single robot in an environment? We can think of the simplest environment. We have a Gaussian distributed light intensity in the center, and we kind of put a single robot in the center of this kind of environment. And what will happen to this robot is that this will move away from the initial point, right? It is started. Of course, it's subject to rotational diffusion. It will rotate around, and its velocity will change according to the light intensity it's measuring. What will happen is that if the light intensity is very high in the in the center, this means that the robot will start slow, right? And it will move faster and faster as it's getting out. Is this correct? What will happen is that, for example, in this case, if the robot has positive delay, it's been displaced from the center. It's actually having a lower light intensity, but it's using the value from the past where it was here before. It's kind of still moving slow, even if it has displaced a little bit. It's kind of a delaying. It's kind of increase in velocity. This creates kind of a behavior that for positive delays, particles stays longer in this kind of an environment. Inversely, if we have a negative delay, what will happen is that as soon as the particles measured intensity of the light is decreasing, because it will only decrease if we start from center, what will happen is that the particle will extrapolate even further the light power reduction and start increasing its movement velocity even faster. This will result in for the particle to get away from the center a lot faster if we start from the center. And this is the case with no delay. So the particle is adjusting its velocity with no delay. Okay, and this actually is a little bit less intuitive than what I told you in this slide, but you can think about the single robot case in a kind of a valve. So think about if the particle has now some limitations. So we have a kind of arena that the particle cannot get out of this region, and the center is very high light intensity. The outside is not as high. It's kind of no light intensity measure. This means that the particle will move faster here and slower here, right? Is this clear? Because when we measure more signal, we move less. When we measure high signal, we move more. This will naturally be in a way that the particle, this is a distribution of a particle with no delay. A robot that is adjusting its velocity with light intensity measured with no delay. This will create naturally a distribution that is a little bit more in the center, because the robot is moving less there, moving slower there. Once it's reaching there, it will take more time to get out. But once the robot is here on the edges, its movement speed is a lot higher, so it will take less time to get back in the other region. It's kind of, I think, semi-intuitive. What happens is that if I introduce a positive delay in the robot's motion, I can actually tune this confinement. You see that if I have a robot with positive delay, what will happen is that it will spend a lot more time in the center of this high light intensity region. This is a little bit less intuitive. That really one needs to numerically experiment and see this. And also, if we have a negative delay of this single robot case, what we are going to observe is that the particle will spend more time at the edges. It's a lot less intuitive, but it will spend a lot more time in the borders, the area with less signal than the center. So that the idea here is that just with playing with a single parameter, which is the delay, everything else is the same. We have the same kind of rotational diffusion coefficient with all the robots. We have same kind of function, velocity adjustment function with the light intensity or the signal that is measured. But what is changing is the only thing is that how I actually process this signal with delay and apply my feedback correspondingly, my behavior can kind of switch from one to another. I kind of tune the behavior of this robot in a way that it should go to an area with higher signal or an area with less signal. Is this clear? So this is kind of a result of this kind of robots. Of course, this can be generalized or can be used in a more advanced way when we have multiple robots. Here, the only difference is that from the single robot case, here we have a lot of robots. Each one of them like have their own signal. That is kind of is a Gaussian profile signal that is going from each robot, and each robot is measuring the total amount of signal generated by other robots, but not itself. Is this clear? So every robot should not concern the light from should not concern the light from others, but only from itself. And this creates kind of the sensor, the signal that is measured by each robot, and they are kind of adjusting their velocity according to this measurement now. It's not an external signal or light field, but it's the signal, the cumulative signal that is coming from all the other robots surrounding them, okay? And then they kind of follow the same idea. If they measure high signal, they move slower. If they measure low signal, exponentially, their velocity decays. And if they act with no delay, eventually they come close to each other. What happens is that if they act with positive delay, as a result, they come closer to each other. They kind of accumulate or group together more. And if they kind of apply negative delay in their velocity adjustment mechanism, they kind of get further away from each other. So if you think about it, this is very useful. Why? Think about in a disaster environment where you have to make search and rescue for the robots. First, they need to disperse away as much as possible, right? And as soon as someone finds something that could be rescued, it should kind of call all the other robots into that area. What could be these kind of delay the behavior adjustment with delay can be very useful for these kind of purposes. And this is actually experimentally done. Again, with Mite, I am advertising Mite today all day long. And here is the experiment robots that you see here. Here are the signals that each robot is kind of generating a signal, and it has kind of these sensors that is also measuring the signal. And what happens is that it's designed in a way that it can't actually, its own sensors can't see the signal generated by the robot itself. It can only be sensed. The signal can only come to the sensors from the other robots. So the light sources are a little bit outside and the sensors are more a little bit inside. And you see that these are the robots' behavior for positive delay, and these are their behavior in negative delay. And this is not just one case that they happen to just randomly come closer to each other. This can be actually quantified by repeating the experiment many, many times. And these robots kind of switch behavior if you change the sensory delay that they are applying or adjusting their velocity, okay? So this is a very novel idea, because from a very simple idea, very simple simulation, what do we have? What are we simulating here? A robot that is moving in 2D, right? And adjusting itself with rotational diffusion. The only thing that is changing is that in the dynamics is the velocity, and that is changing according to the signal measured. And we apply a delay to it, and we get very novel different behavior just by changing one parameter, that is the delay. This is what, do you prefer I take it down? Are you sure? Okay. I forgot again, I was in Sweden. People love it. Anyway, yeah, so this is the novelty that is with the complex systems, that the individual behavior of a robot is not complex at all, but the group behavior can totally be tuned by changing this a single parameter, that is the delay parameter. And of course, one can design, these are the simulations, but from the same paper I just showed you, is that you can design a different function. You don't have to follow the same kind of, the simplest case with the velocity function as a function of intensity. You can kind of change, and with the changed velocity function as a velocity as a function of measured light intensity, you can kind of get different behaviors. This is the case of the single robot case with a light source in the middle. But you can also do the same with multiple robots. These are some simulations that you see here, that if I use this kind of signal, this kind of velocity as a function of light intensity that is measured, we kind of get this kind of behavior, we kind of get this kind of, so we can kind of change the cluster size, average cluster size of, or the clustering speed of the robots. We can tune all these by just changing or manipulating the behavior of this velocity adjustment function. You can also try to come up with your own that is kind of creating a novel or unique behavior of these robots. Is this clear? Yeah, okay. So I think this, I can, for this lecture, since I don't have any videos here, I can show you the animations. Let me see here. So here also from GitHub. I mean, I won't, of course, I don't show you for each lecture these ones, but you can kind of go and play yourself. Here we have one parameter only, that is the sensorial delay. And you see that if I apply, it's very difficult to see from this example. You have to like watch the system a long time. But if I apply a positive delay, you see the particles here and there coming closer together and make these clusters of 3, 4, 5, 6 robots. And if you wait longer and longer, you will see that they come closer together. And of course, this will happen. This will not, there is not a critical behavior here. It's not like that if I have the delay 0, it will be no clustering. If I have the, but it's already less clustered if you can see it. As soon as I put the delay 0, and if I put the delay to a negative number, after a certain time, you will see that they're getting kind of more and more dispersed away from each other, except that sometimes a few of these particles get very close and it takes a bit of time for them to be able to kind of disengage. You can actually, try to see how these simulations are done, or you can actually, I highly recommend you actually don't look at the code. You first kind of try to do it yourself. And then if you get stuck whenever you want to apply a certain parameter, implement something that doesn't work for you, and then you go and look at the code. Because it's, if you look at the code, the problem is that you're not going to learn a lot. Once you have a new task that you don't have a sample code for, or your project, for example, that you don't know where to start with, we don't have an example code that help you with the project. So you kind of need to understand the kind of algorithms behind it. But even if you have completed the project yourself, you can still go and look at the code to understand what could be done differently, to have another opinion, have another kind of idea how it could be done. And also, I can highly recommend you at least have a look at one of these codes, so you kind of understand how you can kind of this is not, no, please. Yes. Okay. So it is, let's see. So there are always the algorithms that you need to understand. You can look at the code also from the perspective of how you can actually animate things. It is important to be able to animate, especially within the realm of simulations, because experiments, if you are making experiments or observations, you can always show them what you measure, what you observe, what is your camera recording, right? Theory is a little bit more complicated, but the power of simulations is you can get a lot of results. And if you can animate them, it's always very useful and intuitive way for people that you show the simulations to understand what is actually going on in real life. So especially for your projects, you may need to create, it's highly recommended that you kind of make animations of your project so that it's kind of use the novelty of making simulations, but also show it to the audience in a way that is appealing, and then they won't get bored. Are there any questions for here for this chapter, sensory delay? So I think we have a little bit of time today. So I want to just make sure that I have explained this clearly. These were all my slides actually for this. So that here is this slide is the fundamental idea, and here is the how I adjust my velocity. So this is actually not a very complicated chapter, but you just need to simulate correct the interaction between multiple robots. And you have multiple robots. You have to kind of create a map of light intensity, but whenever you kind of measure it with a single robot, you need to subtract the one that is generated by the robot itself. You can kind of make it with one kind of using a single. You first calculate the overall signal in the entire grid or the map created by every robot, and then whenever you are going to measure one of them, you kind of subtract the one this one is generated at the generating in the center from it. So you kind of subtract a little bit. Is that clear? So instead of kind of calculating for each robot, maybe actually that is what I'm doing in the example code, but you can actually make it even more efficient like that. So you kind of calculate everything and then just subtract the one that is generated by each robot. And also it's useful to kind of come up with your own functions. What kind of, how can I actually modify these functions of the robot's movement speed as a function of the light intensity or the signal that is measured? And how can I modify the velocity and what kind of behavior do I get as a result? Okay, is everything clear? Yeah, okay. If there is no more questions, these are all my slides for this chapter. I can maybe take questions. Are there questions in the chat? I don't see any questions in the chat. Okay, maybe if you have any questions about the rest project homework. No? Okay, then I complete this lecture as well. Thank you.